My name is Mama AIMAN bin Mama SHAHAR, and I will be showing for the simulation of case A. The parameters for the repeating sequence has been set as shown. For the result of the simulation, as you can see, in first quadrant, positive speed, positive voltage. In this quadrant, the motor is running in the forward direction and is being supplied with a positive voltage. This quadrant represents the normal operating region where the motor is running in its intended direction. In second quadrant, negative speed, positive voltage. In this quadrant, the motor is running in the reverse direction while still being supplied with a positive voltage. This quadrant is often referred to as the regenerative braking region. Here, the motor acts as a generator, converting the mechanical energy of the rotating shaft into electrical energy and feeding it back into the power supply. This braking action helps in decelerating the motor. In third quadrant, negative speed, negative voltage. In this quadrant, the motor is still running in the reverse direction, but the voltage supply to the motor is now negative. This quadrant represents the region where the motor is being actively reversed using reverse polarity voltage. It allows for controlling the motor speed and the direction accurately. In fourth quadrant, positive speed, negative voltage. In this quadrant, the motor is running in the forward direction, but the voltage supply to the motor is negative. This quadrant also represents a regenerative braking region where the motor acts as a generator, converting the mechanical energy into electrical energy and feeding it back into the power supply, resulting in deceleration.
For the case B, this circuit has been used to test rate speed and analyze the controller performance if the speed rating is exceeded. Based on the circuit, only speed that will be changed to define what happens if the controller speed change increase than the actual value. After constructing this circuit, the amplitude value in the signal generator has been set to 1470 RPM to define the result for actual value. Then we run, and the result will show like that. As we can see, the blue and the yellow line at speed graph are synchronized. Then we change the value of the amplitude in the signal generator to 1800 RPM. Then we run, and the result will show like that. From the graph, it shows that the yellow line is not synchronized with the blue line. This is because the blue line is generated by the signal generator, which is set to 1800 RPM, while the yellow line is the output from DC motor drive. Therefore, the actual speed gain are slightly lower than the signal generated.
In this case, the equation asks to show that the motor can be satisfactorily controlled beyond its rated torque and analyze the control performance if the rating current is exceeded. This circuit has been used to analyze. For the first step, set the value of the amplitude of the DC voltage source to 220 volt. After that, you have a function like this that we calculated before. Then we run the simulation. The graph for the torque will show like that. It shows that the motor could not be satisfactorily controlled beyond its rated torque. After that, we change the value of the amplitude of DC voltage source to 400. Then we run the simulation. The graph for the torque show like that. Then we decide to change the value of inertia and friction while remain the value of motor voltage rating as 220 volt. The value for integral gains constant and torque proportionally remain the same. Then calculate the new transfer function and gain constant. Change the value in the circuit diagram. Then run the simulation graph. Like that. The value of new torque load is 10.45 Newton meter. Then we run the simulation. The graph shows that both current and
Hi, Assalamualaikum. My name is KHAIRUL and I will explain about case D simulation. For case D simulation, we need to calculate the efficiency of the system by using theory calculation and also the simulation. In the simulation, we need to change the constant to the step pulse block, and the setting for step pulse is the step time is 0, the initial value is 0, and the final value is our torque that we get from the calculation, which is 10.458. And we also need to change the DC voltage to 220 that given in the table, and the signal generator, the speed is 1470, the rated speed that given in the question. Then after all the parameters insert into the system, then we run it for the 4 second stop time. So from this value, we can find the efficiency through the calculation using the same formula. The efficiency formula is still the same, P out over P in multiplied by 100, and we get the efficiency nearly to the theoretical calculation that we calculate in the early simulation. It is 88%.